Cool. Well, thanks very much for the introduction, and yeah, thanks so much for organizing the conference. It's been really good fun. So I'm going to be giving a talk which is intentionally very confusingly titled "Learning to Discover Learning Algorithms," and in particular, as you say, talking about this new piece of work that we've recently put out called DiscoGen, which you can have a go at trying yourself or check out the code. I'll put this up at the end as well so that you can kind of see where to go. Just quickly, a little bit about me. So, as you say, I'm a PhD student at Oxford, working with my two supervisors, Jacob Forster and Shimon Weitzen. My research has broadly fallen into topics that are probably quite relevant to the people here: algorithm discovery, open-endedness, and I also like to dabble quite a lot into your more conventional deep reinforcement learning in games and robotics and all of that. I was previously an intern at Wave, which is a self-driving company, and in a few weeks' time, you'll see me as an intern at Meta in London. Okay, so this whole talk is going to be about automated discovery of machine learning algorithms, and I just wanted to flash up a couple of things which show how important this is nowadays. We're seeing a bunch of these companies which are being founded to do exactly this. Of course, Recursive have just raised more money than I ever thought possible for a new company to explore recursive superintelligence. But also people like Sakana and Anthropic have been talking about this as well. I just put up this little tweet from Jason Weston as well about trying to make this new paradigm consider humans as well in a kind of co-superintelligence. So check that out if you're interested. But all of this stuff, I think, is super exciting, and it's a really good motivator for the piece of work which I'm going to be talking about, which was just accepted to ICML. And it's a paper called The Procedural Generation of Algorithm Discovery Tasks in Machine Learning, or as we affectionately call it, DiscoGen. Obviously, there's a load of people whose work has helped contribute to this, and I can't take full credit. So thank you to all of these people as well. Okay, so what are we really talking about here? I think it's worth thinking about this discovery of machine learning algorithms in the context of meta learning. Maybe that's just how my brain works, given it was my background. But in meta learning, we generally consider two separate loops. So we have the inner loop. In this case, it's a reinforcement learning training loop. This could be train an image classifier. It could be training a language model. But crucially, this is considered on the lower level. And when we're thinking about meta learning, we start to consider some sort of higher order meta loss and meta updating, which is changing something about the inner loop. So it might be discovering a new optimizer for training a neural network, for example. I think that's maybe what the swarm that's running at the moment is trying to do. Discover optimization algorithms. It might be optimize network architectures or discovering new loss functions or whatever. But the point is, we're learning how to do the machine learning itself. And there's a bunch of benchmarks which exist at the moment to try to work out how well current agents perform at solving these kinds of problems. I'm just going to flash up a few at the moment: Errors Bench, RE Bench. There's loads. Emily Bench is probably the best known. But I just want to really stress at the moment, in addition to some flaws that I'm going to talk about in a second, all of these problems, all of these benchmarks, are very, very limited. We're talking 10, 20, 75, 100 unique problems. And as we all know, the kind of one dominant driver behind the advance of AI in recent years is the ability to access more data for optimizing. So I really just want to ask the question, how could we possibly learn from a set of 50 problems and then evaluate on that same set of 50 problems without having any kind of leakage or whatever? It's just not practically possible. It's not going to work. There are some other things that I just want to stress about these benchmarks before talking about DiscoGen. So, for example, there was someone who asked a question in the chat yesterday. I can't remember who it was, but they were asking about whether agents are being evaluated on the same problems which they're discovering the algorithms for. Now, in our context, we'd call that the meta-train, meta-test split, because we're thinking about this on the meta level. And crucially, none of these past benchmarks consider a meta-test separation. And people have kind of just gone with that. When, if you think about anything in machine learning, take some image classification problem, allowing contamination between the trained test set is obviously going to lead to a very, very flawed evaluation. There's also huge contamination risks because the prior benchmarks are all static. And again, because they're static, we're kind of fixed in what the problems are. So once a benchmark is saturated, it's saturated and we can't move on. Or if we can't get anywhere, then we're basically not going to get an evaluation signal to be able to kind of differentiate between different models and agents. And then finally, I think this is a personal point, but many of these benchmarks, I think, are relatively limited in their scope and diversity, and they generally focus on one type of problem. Maybe it's quick to run problems, Kaggle problems, expensive problems, but crucially, I think covering the breadth of that would be more effective. And so that leads to our solution, DiscoGen. Now, DiscoGen is a procedural generator of these problems. I'll talk about what that means in a second, but crucially, it supports a hell of a lot of tasks. We vary these tasks based on things like the task domain, the parts of an algorithm which we're asking an agent to solve. So is it being asked to solve or to develop a new loss function or an optimizer, or maybe the combination of loss functions and optimizers at the same time, or something else? And a lot of this is domain specific. But also we vary tasks across things like the meta-train dataset, so what an agent's allowed to be running its experiments on, the meta-testing dataset, so what datasets the algorithm which is discovered is going to get evaluated on, and that's going to form our score. So these are held out from the agent. These things that we call backends, which effectively just allow us to kind of minorly change the code, but create very different problems. I'll give an example of that in a second as well. The initialization, so effectively how much code the agent is given at the start. So for each of these algorithm components, do we start the agent off from a standard baseline, or do we just say, here's an empty file, it has to fit into this broad code base, but besides that, just go wild. We can vary these things as well. And then the evaluation type. And I think this is something I think is exceptionally cool. Effectively, we can change what the agent's objective is through configuration files. So is the agent being asked to maximize the performance of its algorithm, which is kind of what people do in MLE Bench? Does it have to match, maybe match the performance of a baseline whilst minimizing the training time used by its algorithm, or minimizing the energy usage by its algorithm? We literally measure the kilowatt hours. All of this stuff is possible. And I think opens up a huge amount of research that we can explore in this. And crucially, DiscoGen is massive. So we have more than enough tasks to learn from, more than I think anyone here will ever be able to get through. And because it's all generated, it's very hard to contaminate. It's not impossible, but the agent will never know exactly what its meta-testing data sets are. So it can't kind of overfit to the specific evaluation set. And then to try and boost diversity, we base all of our tasks on fields rather than papers. And again, I'll show you what that means in a second. Before that, I just wanted to show a quick example of the creation of a DiscoGen task. So this effectively, this configuration effectively defines the entire task, and it's all going to get generated automatically for you. So we specify the task domain, meta-train, meta-test, all the stuff that I just talked about. because the task domain is on policy RL, we're going to initialize the agent with a bunch of on policy RL files. So this includes things like maybe the training loop, some RL specific code, maybe the environment loading, and also a main.py file, which will include evaluation. Crucially, these files are going to be overwritten at meta test time. So the agent isn't able to cheat its evaluation, for example. And then we have discovered files. So because change loss and change networks are true, we're going to ask the agent to develop a new network architecture and a loss function for onPolicyRL. And so these two files get put into their own separate bucket, the discovered files, and these are what the agent's going to be working on. And these are preserved when we move to the meta test. We also automatically generate a description based on all of this information. So the agent's told, here's a bunch of stuff about your meta training data sets. This is what onPolicyRL is. This is what a loss function does. This is what a network does. But we intentionally keep this all very high level such that the agent isn't biased in one way or another in its discovery. And then finally, at separate times, we create these meta training or meta testing data sets. So in say like in image classification, this might involve loading in CFAR and ImageNet at meta train time and like MNIST at meta test time. But crucially, these happen at distinct times. And I said there was a lot of tasks. When I was flashing up all of these benchmarks earlier, I think I was saying there was like 10, 20, 50. I think they peaked at about 100 unique problems. In DiscoGen, we have a support over 100 billion. And each of these is an entire machine learning problem. So for example, in language modeling, it might be train a language model from scratch. That's actually based on the NanoGPT code base. You'll notice it is very dominated by onPolicyMal. So we also consider the median, and even in terms of median per task, there's about 100,000 unique problems. And the goal is to use all of these to optimize agents, right? I'm kind of not content with just taking an off-the-shelf model, shoving it into a scaffold, and calling it a day, and making our auto research run forever. Because to me, that's what this kind of little, I don't know if you can see my cursor, but that's essentially what this little loop is in the middle of the screen, the meta loop. I want to make the agents better at doing this process, which effectively means that we need to add an extra loop on the outside. This is now talking about the meta level, or the agent optimization level, we call it. So crucially, in the meta loop, the agent's going to be interacting with its meta training data sets over and over to develop an algorithm. And then at meta test time, this algorithm is run on held out data sets to give a signal which allows us to update the agent. So that we don't end up overfitting, which we do observe. We can then use DiscoGen to constantly be sampling brand new tasks at every step of this outer loop. And then just to make sure that I've confused you all enough, we also need to make sure that we have something to evaluate the agent on. And that gives us Disco Bench, which is an agent evaluation set. I should say, when we say ADA, we're talking about algorithm discovery agents. And so even at eval time, there's still a meta loop. The agent's still doing experimentation, but crucially, it's doing it on held out tasks now. And you might be thinking, I've said there's 160 something billion tasks. Are they actually different? We try and explore this in the paper through rank correlation analysis, and we find that yes, they are. There's a kind of nice pattern where some tasks correlate with each other across different models, but crucially, they don't always correlate. So it's kind of a nice blend of correlation but low redundancy between the tasks. And you also might be thinking, is all this meta test nonsense actually important? And I think the answer is solidly yes. So we did the same analysis, this rank correlation heat map on just the meta training data sets. We cluster, and then we look at how this transfers to meta test, keeping the same clustering, and we find that the structure completely breaks down, suggesting that the algorithms that were best in meta train are not necessarily the algorithms that were best in meta test. And so I think this alone should be proof that if we want to discover good, novel machine learning algorithms which generalize, existing benchmarks are just completely insufficient. Okay, now I've talked a lot about wanting to do this agent optimization stuff or meta learning. And so you're probably all behind your screen saying, he's talked a lot about this, but he's not showing us any results. So does it work? Crucially, can we use DiscoGen to learn to discover? And the answer is yes. Otherwise, I guess we probably wouldn't have a paper. Right now, we consider prompt optimization. So we have an automated prompt tuning loop based on the Disco pop code that Rob mentioned yesterday. And we want to explore whether adding more tasks is helpful. So if we have the same optimization budget, but we kind of spread that over more unique problems, do we get better performance to these held out Disco bench tasks? Now, I'm going to show you kind of two things in distribution domains and held out domains. So we explore this both for kind of 10 of those 14 that I showed in a table earlier. 10 of those domains are included in the ADA optimization process. And we find a very, very solid pattern where as we add more tasks, the agent performs much better in meta test. Crucially, not in meta train, which I think is very interesting. But in meta test, the pattern is monotonic. But we also find in held out domains, so not only have the tasks not been seen, but the fields themselves haven't been experienced, that as we've increased the number of tasks, the performance of the agent improves. I appreciate this is still kind of small scale, very, very early stuff. And hopefully we can expand this much more in the future. But I think this is a very nice early sign of life that this sort of meta optimization actually does work. And there's a lot of paths to go from there. And so based on that, I just wanted to pitch a couple of big ideas that we kind of have come up with as we were developing the project. These are pitched in the paper, but I think might be of interest to some people here. So the first one is extending this learning to discover work, doing this meta learning, but trying to explore maybe other approaches for doing so. So things like reinforcement learning is an obvious next step. Maybe doing a more principal prompt optimization approach than what we've explored, and also automated scaffold search. So things like the Darwin-Gödel machine, hyperagents, but over these very large very large task spaces. And crucially, this stuff gets very, very expensive very, very quickly. We're no longer talking about SWE bench style problems where the dominant cost is the agent running. Instead, now the dominant cost is having to train a language model for 6 hours before you can get a score out. And so we need to think about how to do this without blowing our budget. One very, very obvious thing to do is explore curricula. So you can see here that we find that as we add more modules in a certain domain, the success rate, literally the ability to produce a successful algorithm, decreases. So there's obviously various kind of gradients of difficulty between tasks that could be explored and exploited to maybe sample more difficult or learnable problems through methods like unsupervised environment design or sampling for learnability. The next thing that I want to pitch is somewhat similar, but focusing not on performance, but efficiency. So most research right now focuses on discovering the best algorithms. But as I said, in DiscoGen, through the configuration file, you can specify what the performance objective is, and performance doesn't have to be the only one. Instead, you could look at efficiency, so the energy used by the discovered algorithm to train, which I think is super cool. Like if we could shave 10% off, I don't know, the training loop of an LLM, that would be crazy. But also things like the speed. So this is very much like the kind of speed running things that we talked about earlier. We also offer support for low memory, so minimizing the peak memory used by a training algorithm, and also the length of the code. So kind of you can just put in code golf and the agent's evaluation metric becomes the size of the files that it used to discover, which I think is kind of cool. We support all of this out the box. You can do this super easily. Memory and CodeGolf is currently in a PR and going to be merged this week. And I think it's interesting to think about whether there's interesting inductive biases that you could inject into the agent to maybe make it better at one or the other of these. And then finally, maybe the most mental idea that I'm going to pitch is algorithm world models. Essentially, the question is if we can search for algorithms and evaluate those algorithms without ever having to train a model using the algorithm. And the solution to doing that is to develop a world model. But the question is, like, how can we actually get this? We need a load of data, which is comprised of algorithms, the data set that the algorithm was run on, and the performance that the algorithm obtained. And then we can train a world model, maybe it would be fine-tuning, similar to the Meta Code World Models paper, to predict the performance based on the algorithm dataset tuple. And then the cool thing about that is without having to kind of use a GPU, we could just hill climb in the world model, much like model-based RL, and hopefully only have to train a final model at the end to kind of like test the final algorithm, which obviously could lead to some huge energy savings. But yeah, thank you very much. I hope you found this interesting. If you want to check out the code or the paper, check out these QR codes, and feel free to send me an email or a message on Twitter if you've got any questions as well.
Yeah, thank you very much, Alex. It was a really interesting talk. We have time for some questions. I'll read them from the chat. So the first question is from Alistair Chung. He's asking that just DiscoGen showed that a more general ADA exposed to 30 tasks could beat the final performance of a specialist. What new search behaviors did the generalist learn that specialist ADA was lacking?
So this was kind of interesting. It very much followed the pattern that you would expect. Obviously, this was all in prompt tuning. So if I kind of focus on the different prompts that were discovered, there was a very clear trend from 1 to 5 to 10 to 30, where at 30, you were starting to see prompts that emphasize very good general kind of research processes. So it would say, do one thing at a time, experiment with this, try to do this, try to, maybe be very novel at the start, and as you're starting to run out of budget, don't do that. The prompt at 1 ended up just saying, you are designing an RL loss function for this environment. Especially because we had this asymmetry where the thing that was developing the prompt was a much more powerful model, so that was using Claude, and it was literally saying things like, for the loss function, this is all of the code that you should write. So I think the crucial thing is at higher counts you started to see much more general principles being pushed.
Thank you. And we have time for one more question. I'll read it from the chat. It's from Richard. It's on this the same vein. So how do you ensure that training an ADA across such a diverse and heterogeneous tasks via DiscoGen actually produces transferable skills rather than a jack of all trades, master of none situation?
Yeah, that's a very interesting question. I think kind of the obvious response to that is the paradigm of AI is that scale always wins. And so if you have a model with sufficient capacity, it's very likely that doing this large scale training should lead to better performance. Now, I think there's a caveat there, which is we should be there's a big difference between I think there's maybe a talk later on discovery at test time training, which is very much about trying to develop specialists, and this, which I would almost call like train time training or whatever you want, maybe like a mid-training step or a fine-tuning step, in which we want to train models to have good research skills. And I think it is very apparent that there are good research approaches which are transferable across settings. And then there is very, very specific knowledge, which maybe you would prefer to emerge at test time. And at that point, yeah, like having a specialist obviously makes sense. Like in humans, we have the scientific method, and then we have a professor of a very, very, very niche field. And I think that's kind of the difference between those two things.
Okay, so thank you very much, Alex.